All right, so in this example, we are going to find the exact value, meaning we should not be using a calculator and we should not be putting a decimal as our answer. We should be finding something that is exact to infinitely many decimal places, which in many of these cases involves a radical, and more importantly, the square root of a prime number, which is irrational. It cannot be written as a fraction, and so the only way to write it to infinitely many decimal places is to make sure that we are keeping it in radical form. So using the double angle formula for cosine, this 1 minus 2 sine squared of theta looks awful lot like cosine of 2 theta. Now I'm using this in the opposite direction. Using this in the opposite direction, which is fine. I just want to remind you that these formulas work in both directions. So this 1 minus sine squared of pi over 12 can be written as cosine of 2 times pi over 12, which is cosine of pi over 6. And if we think about our unit circle, cosine of pi over 6, 6 is the bigger number, so that's a smaller angle. So I am farther to the right than I am up. Cosine is the x coordinate, which means I am farther to the right, so x should be bigger, which is going to be my root 3 over 2. And this is an exact value because it's accurate to infinitely many decimal places because it is written in radical form. All right, so now we're going to verify an identity using some of our double angle formulas. So this one's a little bit sneaky. And again, it looks like, it definitely looks like the right side of this equation is the more simplified side, but I'm going to argue that the left side is less simplified. Or sorry, it looks like the right side is less simplified, but the left side is the one that's less simplified. And the reason for that is both of these have just an x inside them. Whereas on the right side of the equation, we have a 3x. So this left side is the less simplified side. So I'm going to start on the left side. And I'm going to use the double angle formula, and I'm going to use it sort of sneakily here because I'm going to also use the sum formula for sine. So sine of 3x I'm going to write as 2x plus x. And so I can use the sum formula for sine, and the sum formula for sine is sine of 2x cosine x plus cosine 2x sine of x. And now I can use the double angle formula here, and I can use the double angle formula here. And so the double angle formula for sine is 2 sine x cosine x times another cosine x, plus the double angle formula for cosine x, staying focused on the final answer here. The final answer just has signs in it, and so I'm going to want to use the double angle formula for cosine that only has sine in it. So I'm going to use 1 minus 2 sine squared x times sine of x. And so what I have is 2 sine x cosine squared x plus, if I distribute this, I get sine of x minus 2 sine cubed of x. So this is getting closer to our goal here. We have minus 2 sine cubed of x. We just need another negative 2 sine cubed of x. And what I'm noticing here is that this cosine squared of x can be rewritten as, using the Pythagorean identity, it can be rewritten as 1 minus sine squared x. So this is 2 sine of x times 1 minus sine squared x plus sine of x minus 2 sine cubed of x. And if I distribute this, I'm going to get 2 sine of x minus 2 sine cubed of x plus sine of x minus 2 sine cubed of x. 2 sine of x plus sine of x is 3 sine of x, and negative 2 sine cubed minus 2 sine cubed is negative 4 sine cubed of x. And so my final answer matches the right side of the equation, and I have verified this identity. And I need to do the algebra out. I can't just say that I've verified the identity without showing any work. So I need to show the work to get my final answer. So I will see you in the next video. We're going to prove the power reducing formulas, and then we're going to use the power reducing formulas to help us rewrite an expression.